All right. Well, I just want to start by saying how honored I am to be included in this lecture series. I am disappointed not to be in B75 lecturing in the same place where so many influential people lectured before me, but one of these days, perhaps we'll get there. But I'm very excited to be with you virtually. I thought it would be a great idea to start by first reflecting on my time in CEMS. Those were very formative years in my life. So I arrived on campus in 2005 with my soon-to-be wife, Allison, now Allison Tisdale. We were young and baby-faced. We are all grown up now. Allison is now Director of Protein Engineering at Immunitas Therapeutics in Cambridge. And I, as you just heard, am a professor in chemical engineering at MIT. We made some lifelong friends during our time in Minnesota. This was the famous annual Halloween party at the Douglas House. We had 5 classmates who rented the same house for 5 years in a row on Douglas Avenue. And their house was sort of the home base for just about everything social that we did. There's a picture of me celebrating at Sally's after successfully passing my oral exam. And some of these people have remained lifelong friends to this day. I started a family while in graduate school. Allison and I got married, as I just mentioned. We also had our first child while I was in my 5th year of graduate school. We were not always the model of maturity. We were young, but everyone successfully survived until middle childhood at least. This is my daughter, Maddie. She's now in 6th grade, and my daughter, Bryn. This is Maddie when she was an infant, born in Minnesota. And this is Bryn, who's in 4th grade now. I scared away all 3 of my PhD advisors. So I had 3. I was triply advised for my PhD thesis, which was a fantastic experience, and in all honesty. Ire is now at NYU. David Norris was the first to leave. He went to Minnesota, and then I was co-advised as well by Xiaoyang Zhu in the chemistry department, who left to go to Austin first and is now actually at Columbia University. One of the highlights was actually soon after in my last year of my PhD, I had a high-profile paper that attracted a lot of media attention and was even appeared on the local Sunday morning news program on the Minneapolis Channel 9. So hopefully you can hear this sound. This is a video my wife took of the screen while I was on TV.
The horizon and coming fast. And joining us to explain the breakthrough is Dr. Will Tisdale, sorry about that, Will. Just received his doctorate, earned it, not received it, earned it, right? 2 days ago. Doctor, thanks for coming in. Thank you. Appreciate it. Let's talk right away. Let's talk about your breakthrough that your team had when it comes to solar power. Tell us about it.
Yeah, so conventional solar cells only convert about 15% of the sun's energy to electricity.
So a lot of unused energy.
Exactly. And a lot of that excess energy gets wasted as heat. And what happens is when sunlight strikes a solar cell, it knocks loose these electrons that move very quickly and generate electric current. And scientists call these electrons hot electrons. It's been known for several years that if you use semiconductor nanocrystals, you could possibly slow the loss of this energy as heat.
Okay.
What we were able to show is that you could actually pull these electrons out of the nanocrystal before they cool down.
So lots of fantastic experiences, lots of firsts during my time in Minnesota. And I look back on all of that fondly, and it has all profoundly shaped the rest of my life. So I am thankful to CEMS for the huge role that you played in my formative years. So what have I been doing since? Graduated in 2010, went to MIT first to the electrical engineering department for a postdoc. Interviewed all over the country, thought that we'd be moving somewhere else for faculty position, but was fortunate enough to get an offer from the chemical engineering department at MIT, where I've been ever since. So my group at MIT is largely interested in solution processable semiconductor materials, in particular semiconductor nanomaterials, but we do look at bulk forms of solution processable semiconductors as well. The idea here is that from a process engineering standpoint, we could have significant cost savings and significant manufacturing advantages by moving away from traditional semiconductor manufacturing processes. So you think about fabricating electronic circuits the same way you print a newspaper. Imagine spray painting a solar cell on your roof. The applications here range across widely optoelectronics, cheap, efficient solar cells, electronics on unconventional and flexible substrates. bright, large area displays. These days, these same materials are moving into applications like augmented reality systems and even quantum information sciences, if we can get enough control over the nanoscale properties of these materials. There are two material polymorphs that we work with extensively in my group. I'm going to talk about these two systems today. The first part of my talk, I'll talk about colloidal quantum dots, and then the second part of my talk, I'll talk about our work in halide perovskites. So what is a quantum dot? The picture that I always have in my head of a quantum dot is this cartoon illustration that you see here on the left. It's a crystalline chunk of semiconductor material, 2 to 10 nanometers in diameter, nominally spherical, but could be faceted, could be tetrapod, could be rods, could be platelets. They come in all varieties of shape. They're synthesized via solution phase wet chemistry processes. And as a byproduct of their synthesis, the surface of these nanocrystals is coated with a layer of organic ligands. These ligands are essential to the processing of these nanocrystals because that's what imparts colloidal stability to these particles. If these ligands weren't there, the nanocrystals would aggregate in solution and flocculate out. The surface ligands also provide a handle for us for controlling the functionality of these materials and tuning the electronic properties to some extent. This image in the center here, this is a transmission electron micrograph of a single lead sulfide quantum dot that one of my graduate students synthesized. What you're looking at here are individual columns of atoms. You can count the number of atoms in diameter that this nanocrystal is. It's about 20 unit cells across. If you zoom out in the electron microscope, you see this image on the right. This is a hexagonal close-packed monolayer of lead sulfide quantum dots. We did not template this in any way. These nanomaterials self-organized themselves into this hexagonal close-packing arrangement upon solvent evaporation. If you've seen nanocrystals before, what you're supposed to be impressed by when you look at this image is the size and shape monodispersity. The synthetic techniques we use to make these materials have advanced to the point where we can synthesize gram and even kilogram scale batches of these materials where the standard deviation in the diameter is less than the size of the unit cell of the atom. So every nanocrystal in the batch is the same diameter plus or minus one layer of atoms on the surface. The empty space in between the nanocrystals is not actually empty space. That's the space that's occupied by these organic ligands that have much lower contrast in the electron microscope than the heavy lead atoms in the core. What makes a quantum dot a quantum dot? The reason we give it this special name and don't just call it a nanoparticle is this defining characteristic of size-dependent electronic structure. A bulk semiconductor is characterized by a continuum of normally occupied states, the valence band, a continuum of normally unoccupied states, the conduction band, and then a region where there are no electronic energy levels, that's the band gap. As you shrink a piece of semiconductor smaller and smaller and smaller, nothing happens until you get to the length scale of the de Broglie wavelength of the electrons, in which case interference within the nanocrystal places restrictions on the value of the momentum that the electron can have, which in turn, through the band structure, places restrictions on the electronic energy levels that can be occupied. And so these continuous bands of energy break up into discrete allowed electronic energy levels. And effectively what happens is as you shrink the size of your nanocrystal, you can increase the band gap. You can see this very clearly in the absorption spectrum. Over here on the right, every one of these curves is a UV-Vis absorption spectrum of a different batch of lead sulfide nanocrystals that my student Mark synthesized. The number here indicates the average diameter of the nanocrystals in that colloidal suspension as measured by TEM. And as the average size decreases, the onset of the optical absorption continuously shifts towards the blue. Lead sulfide has a bulk band gap far out in the infrared. So this is the near infrared part of the spectrum that we have tunability in. Lead sulfide is attractive for use in near infrared sensing as well as photovoltaics. Of course, you can see this most dramatically in visible emitting nanocrystals where the photoluminescent spectrum of the material can be tuned simply by changing the size of the nanocrystal. This is not something you can do with conventional semiconductors. With conventional semiconductors, the only way to change the band gap energy is to change the elemental composition. With quantum dots, you can change the band gap of the material simply by changing the size of the crystal. So quantum dots are no longer just a laboratory curiosity. They're already commercialized. You can walk into Best Buy right now or go onto Amazon, as you're more likely to do, and order a Samsung QLED TV. These TVs have indium phosphide quantum dots in the backlight of the display. The highest end Sony Bravia TVs also have quantum dots in the backlight of the display. I think one of the most interesting applications right now, this company Envisage was a startup company out of Ted Sargent's lab at the University of Toronto. They were developing a technology where you would take lead sulfide quantum dots and then spin cast them onto CMOS chips, and it would increase the sensitivity of the otherwise silicon detector out into the infrared. And so this made highly sensitive near IR imaging systems. Apple actually bought Envisage and owns a ton of quantum dot IP, and we think that where they're using this technology is in the facial recognition system. The way the facial recognition system on your iPhone works is it emits infrared light, it bounces off, and then there's a forward-looking infrared camera that's detecting that. And we think that lead sulfide quantum dots are in that device, but Apple's very secretive about what they actually put into their products. Okay. For all of these applications, an absolute must from the material standpoint is size monodispersity. You need all your nanocrystals to be nearly the same size and shape. You can see that in a light emitting application, why that's important, because the color of light that the quantum dot emits is closely related to its size. So if you have a broad distribution of sizes, you have a broad distribution of colors. It's also important from an electronic transport standpoint that if you have varying size dispersity in your array, then you've got a whole bunch of different band gaps in your material. And that leads to an energetically heterogeneous landscape that makes it more difficult for electrons to make it to a collecting electrode, for instance, in a photovoltaic cell, than if you have a very homogeneous energy landscape. In my lab, we synthesized our lead sulfide quantum dots according to a method originally developed by Katam Artiri. It's a reaction of lead chloride and olealamine with elemental sulfur under vacuum or nitrogen at modest temperatures. And if the reaction is successful, you get this very ugly coffee-looking thing. That's because these are near infrared band gap materials, so they absorb all visible light. So not as pretty to look at as the cadmium selenide materials, but very useful. We have begun to be very interested in the surfaces of these nanocrystals. So the size and shape of the cores is something that we can understand well from electron microscopy or from X-ray diffraction. But it has historically been very difficult to understand what is on the surface of these nanocrystals because of lack of good characterization techniques. Recently, Jim Swan, who's another associate professor in the chemistry department at MIT, and I have been working together trying to use small angle neutron scattering to learn more about the surface ligand layers coating nanocrystals. The experiments are relatively simple. We go to a neutron scattering beamline. We look at colloidal dispersions of our lead sulfide quantum dots coated with, for instance, oleic acid on the surface, an 18 carbon chain with a single double bond in it with a carboxylate linkage to the surface. They're usually dispersed in toluene. We collect the 2D scattering pattern and then we analyze it. Here's an example of what the data look like. So this is the scattering intensity as a function of scattering angle, where we varied the deuteration fraction of the toluene solvent in the suspension from 100% deuterated solvent to about 20% deuterated solvent. One of the striking things you see here is all we're changing is the deuteration fraction, but the location of the dominant scattering peak is actually changing. We don't think that the quantum dot is changing in size. There's no reason to expect that. What this is telling you is it's informing on solvent penetration into the ligand shell that's on the surface. And as we change the deuteration fraction from the standpoint of the neutrons, the effective size from a neutron scattering cross-section standpoint is changing, even though chemically nothing is changing outside of the ligand shell. So Sam, our joint student, has developed MD-inspired models where we can determine the volume fraction of the material as a function of radial distance and allow us to access things like the density of ligands on the surface and the penetration of the solvent into that ligand layer. So here's some example experiments we did where we took the same size batch of nanocrystals and varied the ligand coverage on the surface as measured by proton NMR spectroscopy, and then did the neutron scattering analysis. And you can see that we have different concentrations of ligands which this was a proof of principle that verified our proton NMR experiments. One of the things that Sam and Jim have been doing that's particularly innovative is using robust Bayesian inference methods to get really statistically meaningful parameter distributions. So we've been using fitting a many parameter nonlinear Monte Carlo nonlinear model to Markov chain Monte Carlo sampling methods to get cross correlations between parameters, understand which two parameters are interchangeable and redundant with each other, and to get an overall sense of the parameter distribution. The other thing that neutron scattering told us that we had been asking for a long time was about the presence of a thin chloride layer on the surface. So it had long been hypothesized by a lot of circumstantial evidence that quantum dots made in the method that we make them using lead chloride as a precursor have a insulating thin lead chloride shell that's epitaxial on the surface. It's been nearly impossible to characterize via X-ray scattering and electron microscopy because it's epitaxial and because lead is present both in the core and the shell, and it dominates all of your scattering probes. But the chlorine has a very different neutron scattering cross-section, and we were able to unambiguously measure its presence on the surface. Okay. Monodisperse quantum dots do a lot of great things electronically. They also will self-organize themselves into ordered structures. All of these images right here are just spun cast batches of quantum dots where we let the solvent dry. This is not a slow controlled crystallization. The quantum dots are self-arranging themselves like this in just a matter of seconds during the spin coating process. This is a TEM image looking down the 100 zone axis of a body-centered cubic superlattice. And this is the same material viewed in SEM. We got very interested in how these superlattices form. And so my student Mark, who was going up to ChES, the Cornell High Energy Synchrotron source at the time, he happened to be going on one trip at the same time that Detlef Smilgies, a staff scientist there, had just finished fabricating a chamber for in situ X-ray scattering experiments. And so it's a chamber that you can close up, and it has Kapton windows that are transparent to the X-ray, but can enclose a chemical environment inside the chamber. And so you can understand in situ processes that are going. And so the experiment my student Mark did is he took a droplet of the colloidal suspension of lead sulfide quantum dots in toluene. He dropped it on a smooth silicon surface. He put a few extra drops of toluene in the chamber so that there would be appreciable toluene vapor pressure. He closed up the chamber, he closed up the X-ray safety doors, and he walked out. And then he started simultaneously collecting small angle scattering patterns and wide angle X-ray scattering patterns while he flowed a helium carrier gas through the chamber to slowly dry out that droplet and watch the superlattice form. And here is the data he collected. Ooh, that was the first thing I said when I saw this data when Mark brought it home. I thought this was just about the coolest thing I'd ever seen. You're watching a phase transition happen from a disordered colloid to an ordered superstructure. What's particularly interesting is that the superlattice, the initially superformed superlattice, is not the final superlattice you wind up with. That the superlattice structure evolves and changes over time. You can watch these peaks merging into each other. You see at later times, the whole scattering pattern moves outward. That expansion makes sense. An expansion in reciprocal space is the same thing as a contraction in real space. And we assume that that's just associated with drying, removal of residual solvent. But there's something else more complicated going on. Simultaneously, we can coordinate the structure of the superlattice with the atomic scale arrangement of the individual nanocrystals themselves with respect to the laboratory frame through the wide angle X-ray scattering pattern. And what's really interesting about this is you'll see that this one wide angle scattering peak forms up nicely while its neighbor continues to evolve. And so that's telling you that somehow one particular axis, atomic axis of the nanocrystals is well aligned with respect to the laboratory frame, while another axis continues to vary. So there's some sort of coordinated rotation of all of the nanocrystals within the superlattice that's happening during this drying process. So Mark did the painstaking work of indexing every frame of this in situ X-ray scattering experiment. And the overall story looks like this. The initially formed superlattice is a so-called FCC rotator phase. It's an FCC structure where there's no particular orientation of nanocrystals with respect to each other. The very next thing that happens once they reach that FCC configuration is that they lock in their relative atomic orientation. Despite these oleic acid, 18 carbon disordered ligands on the surface, there is some driving force for the atomic planes on neighboring nanocrystals to form an epitaxial registry across lattice sites within the crystal. Once that atomic plane alignment is achieved, then the overall structure undergoes a uniaxial contraction and a coordinated rotation that continuously transforms the crystal from an FCC phase to a final BCC structure through a series of body-centered tetragonal intermediate phases. We had a hard time understanding that initially, how you can continuously go from FCC to BCC. Those of you who have taught undergraduate material science will probably recognize this as the Bain transformation that happens in the tempering of martensitic steel. But if you draw two FCC unit cells in blue next to each other, you can define another unit cell in red here that's a body-centered tetragonal unit cell. And if you have uniaxial contraction along this one axis, eventually just the definition of the unit cell changes, and this red cell becomes your irreducible representation. The really interesting thing here, I think, is that the direction of this contraction is not in the surface normal direction. It's 45 degrees off surface normal. So this is not driven by a surface normal gradient in the solvent density. This is a coordinated transformation of the entire lattice. Mark was nice enough to make these real space renderings of the crystal. And if you look from the unit cell standpoint, there's actually not a whole lot that's going on. Once they achieve this locked in phase, it's just a uniaxial contraction. But what's interesting is throughout this transition from a BCC structure to an FCC structure, there's a 9.5 degree difference between the 110 close packed plane of the BCC structure and the 111 close packed plane of the FCC structure. And so for the whole superlattice to remain in contact with the substrate, the entire thing has to rotate during this contraction process. Okay. So that was all super interesting, but that was a single experiment. We had lots of questions, lots of follow-up experiments that we wanted to do. And so a new student, Sam, comes along and tries to reproduce Mark's beautiful Nature Materials paper and is having a lot of trouble. Sam makes a bunch of batches of quantum dots and can't seem to get the same results Mark got. He sometimes gets an FCC structure, sometimes gets a BCC structure, a lot of times gets something in between. You'll see for the rest of this section of the talk, I'm going to plot things on this cubic representation where we've got the A and B axis dimension plotted versus the C axis. When the A, B, and C all equal each other, that's FCC. At a particular ratio, that's BCC, and then everything in the space in between is a body-centered tetragonal. So Sam was really confused and had a hard time understanding why he wasn't able to reproduce Mark's results. He had the very good idea to check the proton NMR. So this is some example proton NMR. This is our deuterated toluene solvent. Then Sam does another collection where he adds some dibromomethane to the deuterated toluene, which acts as a quantitative standard so that he can quantify the number of protons that he's looking at. And then if he looks at the quantum dots in deuterated toluene with dibromomethane, he sees all of these aliphatic protons out here that are a big mess. But then down here, these are the vinyl protons. So there's this double bond in the oleic acid. So we're looking at the protons off of this. Off of these two vinyl carbons. And there's two peaks. And it's been shown previously by Zager-Hens and John Owens and others that these correspond to bound and unbound ligands. That the bound ligands are shifted and broadened with respect to the free molecules in solution. And so this allows us to separately quantify the number of ligands that are bound to the surface versus the number of ligands that are free in solution. And so Sam, using this information, turned back to his GSAX data, and you can measure the volume of the unit cell very accurately using X-ray scattering. And then based on everything that's in there, he predicted what the unit cell volume would be. And the really interesting thing is that he only got good agreement between his predictions and the measured unit cell volume if he included the free ligand in the superlattice structure. And so based on this comparison, Sam concluded that the free ligand is not getting expelled into a separate phase, but is somehow getting entrained in the nanocrystal superlattice and is occupying space in the superlattice as another constituent. The effect of excess homogeneous ligand is a very recent realization. All these papers are from 2019 here. This is work from Mike Weir's group at Sheffield, where they did some neutron scattering experiments and concluded that some free ligand in solution is associated with, or physisorbed, as they said, to the ligand shell surrounding the nanocrystal. This is work from Nick Kotov's group and Dmitry Talipin's group. So the next experiment Sam did were, rather than these random batches he had made that have very poorly controlled ligand concentration, he did controlled additions of ligand to very well-defined batches. So he made a single batch of nanocrystals. They're different colors, but they're all the same size nanocrystal, just with different surface-bound ligand fractions. So this is a very saturated surface with ligands. This is an undersaturated surface with ligands. And he did controlled titrations, adding free ligand to these different batches, collected a bunch of X-ray scattering data. You're not supposed to be able to learn much from looking at those patterns. What's more interesting is if you look over here on the right. So for the very under-coordinated samples, they tend to form BCC structures. And as you add more ligand to the surface, they push into this body-centered tetragonal phase. If you start with a very heavily coated nanocrystal surface, it starts as FCC and then stays as FCC as you add ligand, but the constant, the lattice constant, just gets larger and larger. Interestingly, not all of the free ligand gets incorporated into the unit cell. There is a period where adding unbound ligand expands the lattice, and then there's a point where you hit saturation, and the more ligand you add, you can't further increase the lattice constant of the superlattice. So the really striking thing here that we thought was that this march through phase space that the system takes as you add more and more free ligand is exactly the reverse process we saw during the in situ X-ray scattering experiments removing solvent. So here, as you remove solvent from the lattice, you go from an FCC to a BCC in a uniaxial contraction. Here, you're going, as you're adding free ligand, you're going from BCC to an FCC, again, as a uniaxial expansion. This is a snapshot of a molecular dynamics simulation that Sam made. The blue are bound surface ligands and the red are free ligands. And you see in the MD simulation that the free ligand molecules associate themselves with the ligand shell, and that more free ligand can associate itself with the ligand shell when there's fewer ligands around the nanocrystal to begin with, up until a point, up until you completely saturate that surface and then additional ligand can't incorporate with the shell. And so the overall picture here is that the free ligand is playing the same role as solvent in the superlattice. It's effectively just a very low vapor pressure solvent that does not evaporate from the material as you evaporate your superlattice. So this was new understanding for us and new understanding for the field, to my knowledge. We are doing ongoing work to try and understand the role of free ligand in mediating self-assembly. We know that the surface ligands are essential to getting ordered superlattices. If you strip off too many ligands, you don't get ordered structures. So it's soft materials interactions are at the core here. Sam has developed some coarse-grained models that can reproduce most of the observations, but those are still under analysis and unpublished at this point. Okay. Colloidal quantum dots are amazing. I've studied them for years. Halide perovskites are really the only other material that has come along since quantum dots that have inspired as much interest from me. And this is for a variety of reasons that I'll try and walk you through. So first of all, what is a perovskite? A perovskite refers to a particular cubic crystal structure having an ABX3 stoichiometry. It's nominally cubic, though most perovskites these days are quasi-cubic. You have, for halide perovskites in particular, you have a heavy metal like lead or tin at the corners of the unit cell, and then they're surrounded by octahedra of an halide anion, chloride, bromide, or iodide. And then because these ions are so large and the heavy metal is so large, there's actually a lot of space in the center of this unit cell where you can fit a very large cation. It could be a large monovalent metal cation like cesium, or it could be an entire organic molecule, methylammonium or formamidinium. And these materials had been known for several decades, actually, but it wasn't until about 5 years ago that someone realized you could make a really efficient solar cell out of these materials. So this is your classic solar cell technology chart plotting the power conversion efficiency as a function of the year the technology was developed. We've got organic photovoltaics that are slowly marching up in efficiency. We've got amorphous silicon, dye-sensitized solar cells. And then over here in yellow, you've got perovskite solar cells. And the perovskite solar cells are shooting up. This is a 2015 review. As of the latest efficiency record, as of September of this year, just the last month, the current perovskite power conversion efficiency record is 25.5%. For reference, the single crystal silicon record is 26.7%. I think at this point, it is no longer a question of if perovskites can surpass silicon in power conversion efficiency. It's just a question of when. The challenge at this point is not the overall power conversion efficiency, but the stability of the materials. And that's where most of the work is right now, that it's going to take some time to prove that perovskite solar cells are as reliable as silicon solar cells. Okay, but this is completely surprising because these crystalline silicon solar cells are very expensive to make. It takes high temperatures, a ton of energy, and a ton of time to crystallize silicon that is nearly defect-free, because defects in these materials are the result of power conversion efficiency losses. In contrast, these perovskites, they're actually spun out from solution or even vapor deposited. They're baked at 100 degrees Celsius or so, and then you can make a solar cell that is as efficient as silicon. So these materials must be full of defects. And for a long time, we thought that what was special about these materials is that they're defect tolerant. The emerging understanding, and this is a school of thought that is highly debated, but one that I subscribe to, is that these materials are not defect tolerant, that they are actually largely defect free. If you do measure the absorption coefficient as a function of photon energy, for the perovskites, you can see very, very sharp onsets in the optical absorption, which indicates that there's a very low density of defect states extending into the band gap. Estimates of defect densities in perovskite single crystals are order 10 to the 10th per cubic centimeter compared to 10 to the 26th atoms per cubic centimeter in a crystal. In thin films, it's modestly higher. If you look at calculations of the defect formation energy, you'll see that these numbers are actually near the thermodynamic limit, that you'll never have a completely defect-free material because you'll always have Boltzmann statistics. There's always some thermal occupancy of the higher energy defective state, but that these defect densities are nearly at that thermodynamic limit. So why is that? Well, the thermodynamics of these materials are even more curious. If you do the calorimetry, you do the experiments, you write down the formation reaction. This is methylammonium lead iodide, the formation from the solid binary lead iodide and methylammonium iodide. You'll see that the free energy of formation is negative, as it should be for a stable crystal. Only it's slightly negative, only a few times kT at room temperature. But remarkably, the delta H of formation, the enthalpy of formation, is actually positive, which is telling you that it's entropy that is stabilizing the crystal, that this is a crystal really unlike other inorganic semiconductors that we've experienced, where the strength of the material is determined by the bonds. In this case, the strength of the material is really determined by the entropy of the overall crystal. And so the picture that emerges is this highly dynamic material at room temperature, weak interatomic potentials, soft anharmonic bonds, a very low activation energy for self-diffusion, which presents a picture of something kind of liquid-like. It is very much a solid, but it's a very, very dynamic solid that can very easily heal defects within the crystal. This is a molecular dynamics simulation of 4-memadinium lead iodide at room temperature. The magnitude of these vibrations are completely unlike you would see in silicon, for instance, at the same temperature. Okay, so that's all why I think perovskites are interesting. Back to the applications. One of the applications people are most excited about that several companies are attempting to commercialize right now is using perovskites not as a competitor for silicon, but as a way to augment the performance of existing silicon solar technology. And the most attractive idea is take a great silicon solar cell that you've already got and put a perovskite layer on top of it. And you can tune the absorption of that perovskite layer so that it's absorbing most of the visible and blue part of the electromagnetic spectrum, and then the silicon solar cell is absorbing the near infrared portion of the solar spectrum. So Henry Snaith and co-workers made a nice publication, a proof of principle device a few years back. And the real interesting thing here is that the perovskite that they made, when they made to tune the band gap bluer, you need to have an alloy of iodide and bromide to shift the band gap to the correct position. And that when you do that, the best performing perovskite formulations have a mixture of different cations, in this case, some 4-memadinium and cesium. Ted Sargent's group came along a little bit later and said, hey, you can do even better if we don't limit ourselves to just 4-memadinium and cesium, but let's add some methylammonium in too. And so these simple ABX3 structures start to become very complicated and have these peculiar stoichiometries that don't seem to make any sense from any first principles reasoning. So one of the questions we asked was, how does the perovskite composition affect carrier transport? So we had a visitor to our lab. This is Dr. Maksud Saidamanov. He's now a professor at the University of Victoria. At the time we did this work, he was a postdoc in Ted Sargent's group at University of Toronto. And Maksud specializes in the growth of very high quality single crystals of varying composition. These are all millimeter and centimeter sized crystals of single crystals of perovskites with different composition. And he worked closely in my group with one of my postdocs, Dr. Chris Williams, who is an expert in a time-resolved photoluminescence microscopy technique for the direct visualization of charge and exciton transport in materials. So this is work that we had, a technique that we had originally developed in the context of visualizing exciton transport in quantum dot thin films and organic thin films. And Chris was working on adapting this technique to try and understand charge carrier transport in non-excitonic semiconductors. So we were not the first to try and study charge carrier transport in perovskites. Many groups have been doing this over the past few years, but this is the type of data that we collect. So this is a two-dimensional map. This is one spatial dimension in the surface plane and another spatial dimension. The idea is you take a tightly focused laser pulse to excite a distribution of charge carriers. They diffuse outward from areas of higher density to areas of lower density, and then recombined and photoluminesce. And if you can visualize with enough time and spatial precision the spreading of that distribution, you can directly measure the diffusivity of your charge carrier population in time. So these are some snapshots, just like I showed you. At early time, you have a narrow spatial distribution. As time goes on, it broadens out. The analysis of this data is not nearly as straightforward as it is in the case of exciton transport. And this is all because of the nonlinear dependence of the photoluminescence on the excitation density. So in this free charge carrier material, bimolecular recombination dominates. That's the recombination of free electrons and free holes. And so because your local photoluminescence intensity is the product of your electron density and your hole density, then your photoluminescence scales quadratically with your excitation density. Well, this is a problem if you're trying to measure the spatial broadening of your photoluminescence, because your charge carrier density is higher in the center of your excitation area than at the edges. So the center is going to recombine faster than the edges, which leads to a broadening of the full width half maximum of your spatial photoluminescence that you measure, even in the complete absence of diffusion, just because of the nonlinear relationship between the photoluminescence and the charge carrier density. So to accurately model this data, to analyze it, you need to solve the full partial differential equation in 3 dimensions, where we're modeling the carrier distribution in 3 spatial dimensions and time. It's a simple transport relationship, just like you learn in undergraduate chemical engineering, just applied to charge carriers in solid. These reaction terms refer to different linear and nonlinear charge carrier recombination mechanisms. We include a boundary condition at the surface that accounts for some surface recombination. And it's important to note here that we're not independently measuring electron and hole populations. We don't know which carrier is doing most of the diffusing. What we are measuring is an effective ambipolar diffusivity and the product of the local electron hole pair density. Oh, this is just more stuff saying we did a very careful job. The initial condition for the simulations, it's a Gaussian distribution in the surface plane, Beer's law into the sample. We have to take into account the convolution of our detector size with the emission. And then we did a lot of work validating our model using some Monte Carlo simulations and then fitting the Monte Carlo simulations with the PDE solution to develop confidence in our model. Okay, so all of that is the how we did it. What did we learn from the measurements? Well, really surprisingly, we learned that in the single crystals, the carrier diffusion does not depend on composition. This was very surprising to us. So here we're looking at 3 different samples. We're looking at methylammonium lead iodide. We're looking at a cesium 4-mamidinium blend, so a binary cation. And then we have a 3-component cation that's an iodide bromide mixture as well. And the diffusivity in all cases is about 0.5 centimeters squared per second. That's very close to what we were expecting based on others' reports, but there was no dependence on composition. We were surprised because these materials make very different efficiency solar cells. Why did we not see a difference in the charge carrier transport behavior? Well, this is because you don't make solar cells out of single crystals. You make solar cells out of thin films. And the thin films are not single crystalline, they're polycrystalline. The size of these domains is about 100 nanometers or so. And when we did the same carrier diffusion imaging experiments on these polycrystalline samples, we saw much larger variation in the data. So in all cases, these are the same 3 compositions, but in thin film form this time. In all cases, the diffusivity is an order of magnitude lower than it was for the single crystal. So that's telling you that, that the grain boundaries already are having a role in disrupting charge carrier transport. And we saw much greater variation among the different compositions. So the carrier diffusion in the perovskite thin film strongly depends on composition. To reinforce our measurements, because we're getting all this information from the time resolved microscopy measurement, we wanted another technique to verify. We did a thin film quenching experiment, which quantitatively within our uncertainty verified the results of the time resolved microscopy. Okay, so what's going on? The overall story here, I think I'm getting a little long-winded in telling the story, but the overall story here is that there is halide anion segregation within the grains, and that the grain boundaries tend to become bromide rich. And the bromide perovskite has a larger band gap than the iodide perovskite in the core. And so because of that halide anion segregation within the grain, that means that the grain boundaries now have a potential barrier disrupting transport across the grains. And effectively what we see, is that the multi-cation perovskites enable a flatter energetic landscape and less halide anion segregation than the binary or single cation perovskites. Perovskites make terrific solar cells. If they're such defect-free, wonderful semiconductors, then they should also make great quantum dots. And indeed they do. The seminal work in this area was out of Maxim Kovalenko's group at ETH. They synthesized cesium lead halide nanocrystals about 5 years ago at this point. This is a now highly cited paper. Many people in the quantum dot community are working with these materials these days, our group included. If you look closely at the absorption spectra of these different cesium lead halide nanocrystal formulations, you'll see that they do not look like the absorption spectra of quantum dots. They look like the absorption spectra of bulk semiconductors, that they're very weakly confined. These cesium lead halide nanocrystals are loosely quantum dots. There's some quantum confinement, but not nearly as much as you find in a cadmium selenide quantum dot or a lead sulfide quantum dot. And we were interested in pushing that further. What if we could make a atomically thin 2-dimensional version of a perovskite nanocrystal? Perhaps then that 1-dimensional quantum confinement could be more extreme than the weak confinement in 3 dimensions. The first time we did this was completely by accident. We synthesized nanoplatelets or atomically thin sheets of methylammonium lead bromide coated with butylamine ligands in solution. It was a byproduct of another synthesis we were trying that we correctly isolated and identified. At the same time we did that, a number of other groups were also working on two-dimensional versions of colloidal perovskite nanocrystals. We eventually got good at making these materials intentionally and published a follow-up paper with a systematic study. We label these materials by the number N, which refers to the number of octahedral layers in thickness that the material is. So the N equals 1 has 1 lead halide octahedra, N equals 2 has 2 lead halide octahedral, N equals 3 has 3. And you can see in the photoluminescence spectrum that for the bulk lead bromide system, it emits in the green. And then as you reduce the number of lead halide layers down to just 4, 3, 2, 1, you get quantum confinement and a blue shifting of the emission spectrum toward the ultraviolet. There are a number of ways to make these materials at this point. The way that we make them in my group is what is most often referred to as a ligand-assisted re-precipitation. It's quite simple. We take all of the salts, we take the lead halide material, the perovskite material, all of the ions that end up in the final structure. We dissolve them in a polar solvent, we add a little surfactant, and then we drop that into a non-polar solvent. And you'll get crystallization at room temperature of two-dimensional sheets stabilized by the surfactant layers on the surface. This is a video of that synthesis. This is just pure toluene, room temperature in the fume hood on the bench top. And these are the precursors dissolved in dimethylformamide along with some surfactant. And you simply drop them in and you instantaneously get this blue emitting structure. You can control the thickness, the average thickness of the material you get by controlling effectively the surface area to volume ratio, by controlling the ratio of the surfactant to the bulk-like precursors that you have in your initial formulation. The structures here, we can learn a lot about them from doing X-ray diffraction. If you drop cast that colloidal suspension onto a solid substrate, all the sheets lie flat on each other and stack, and you get well-defined interlayer diffraction peaks, as you can see here, that are periodically spaced that allow you to very accurately identify the thickness of the ligand layers and the thickness of the perovskite layers themselves. You can control the spacing by controlling the ligands that are on the surface of these nanomaterials. And you control the band gap or the exciton energy by controlling the composition of the material. So this is a double axis image. We've got wavelength at the top, so blue to the right and red to the left, and then photon energy down here at the bottom. The dotted line is the absorption spectrum. The solid line is the photoluminescence spectrum. For the lead bromide system, looking at just the two thinnest members of this family, the N equals 1 and the N equals 2. N equals 1 is right on the edge of the ultraviolet. The N equals 2 is a nice deep blue. If you go up on the periodic table from bromide to chloride, we can push the absorption into the ultraviolet. If you go the other direction, down on the periodic table from bromide to iodide, the emission spectrum moves from the green to the yellow. And if you substitute lead for tin, you can get orange and red emitting nanoplatelets as well. The tin is much more troubling to work with. It oxidizes easily, so the tin has to be handled inside a glove box. They don't look like much under ambient lighting, but under ultraviolet excitation, they are beautiful blue luminescent colors. And you're not restricted to just these discrete peaks by doing any stoichiometric ratio you like. Any alloying, but from pure iodide to iodide bromide mixtures to pure bromide, bromide chloride mixtures to pure chloride, you can continuously tune the band gap of these materials. Since working with the colloidal nanoplatelets, we've also begun doing a lot of work with solid crystals of the layered structures. So rather than going a colloidal route, you can directly synthesize large ordered layered structures of these 2D organic, inorganic halide perovskites. They form extended networks like this that have a very well-defined crystal structure. You can tune their composition. We can make different thicknesses. We can include different ligands, butylammonium, hexylammonium, pentylammonium. We can include different cations, methylammonium, formamidinium, and have a broad parameter space to explore. We synthesized a large family of different thickness, multi-layered lead iodide perovskites. We solved their crystal structures. We did single crystal X-ray diffraction as a function of temperature, and mapped out the full phase diagram of these different materials. This is quite a long, detailed paper that my student Oat worked for about 3 years on with the synthesis and the characterization of these materials. What you can see in a lot of these crystal structures is that the halide octahedra are distorted. They tend to be tilted. It's rarely a purely cubic phase. There's lots of distortion of the halide octahedral network, and that's all determined by the steric hindrance of the organic cations that are bound to it. All of these are looking at the change in the structure across a near room temperature phase transition that was particularly interesting to us. When we did the differential scanning calorimetry and analyzed the X-ray crystallography on these samples, we identified this particular near room temperature phase transition to be a selective melting or an order disorder transition of the organic subphase. That the organic, just like a self-assembled monolayer or a Langmuir-Blodgett film, will undergo a transition as a function of temperature from a tilted ordered state to a more straight disordered state. The same exact things happens in these natural organic inorganic quantum wells, seemingly without perturbing the electronic structure of the perovskite network at all during the process. I think I'm running behind on time. I'm going to skip this beautiful work that Katie Mauck did. She was, well, okay, I'll just tell it fast. So I just want to sum up where we are now. So we've got this picture of a material where electronically the organic subphase is very decoupled from the inorganic subphase. The band gap of the material is determined entirely by the inorganic layer and what its thickness and what its composition is. And then from a structural standpoint as well, we saw that you can really view these a lot like composite materials, that the organic phase can undergo its own structural transformations without significantly affecting the inorganic subphase. So a lot of these indications are that the organic and inorganic layers within this natural quantum well structure are largely decoupled from each other. We wanted to see if that extended to vibrational properties as well. Katie, who's now a professor at Kenyon College, she synthesized a whole series of N=1 lead iodides with variable length alkane thiol ligands. You can see from the optical emissions absorption spectrum that the band gap is not changing. The only outlier here is the C6, which has a different symmetry than the other 5 members. Katie did some great work. She did resonant impulsive stimulated Raman scattering. It's an ultrafast spectroscopy technique where you do ultrafast transient absorption, and then you're looking at these coherent oscillations that are riding on top of your electronic signal. If you separate out the electronic component and extract just the residuals on top, and then take the Fourier transform of those signals, you can extract a Raman spectrum to identify which vibrational modes are strongly coupled to the excited state. And we compared the resonant impulsive stimulated Raman scattering on these materials to the ground state non-resonant Raman scattering spectrum. And I'll jump to the chase at the end and then compare these to DFT simulations. And what we find overall is that the inorganic cage is really dominating most of the dynamics in these materials, that the electronic excited states are determined almost entirely by the vibrational motion of the lead halide octahedra and not by the organic cations. The organic cations, their motion is involved in these motions, but it's really as a spectator ion, that these heavy iodide atoms are pulling along these very light hydrocarbon chains along with them as they vibrate. And I think I will skip this last part right here. This last part was just trying to, can we engineer the organic cation to do more? So all of this is very disappointing that you have this hybrid material, but the organic phase isn't actually doing much. We did succeed recently. This is a collaboration with Sam Stoops' group at Northwestern, where through molecular doping of 1,2-tetrachlorobenzoquinone into a ligand layer that includes a naphthol moiety, the TCPQ and the naphthol form a ground state donor acceptor complex that has a very large dipole moment within the organic subphase. And by controlling the amount of doping, we decided that we could tune the exciton binding energy in these materials. And so by putting different amounts of this molecular dopant into the organic layer, you can take this very strong exciton binding energy and making it weaker. Along the way, we learned a lot about the hydrogenic or highly non-hydrogenic exciton Rydberg series in the absorption spectra. This has been the subject of some debate, whether this is the onset of the band edge absorption or actually the contributions of higher Rydberg states of the excitons. Okay, with that, I will stop and take some questions. Most importantly, in addition to the students and our collaborators, thank you for funding from the US Department of Energy. All of the Perovskite work was funded by, jointly funded by the Physical Behavior of Materials and the Condensed Phase Interfacial Molecular Sciences program. And then the lead sulfide superlattice work was funded by the Neutron Scattering program, also in DOE Basic Energy Sciences. And I'd be happy to take questions.
Okay, Will, thank you very much. That was really fantastic. You have to imagine B75 filled with applause now. This is the only part that we can't fully capture. If anybody has a question, please go ahead and put it into the chat box. Just put your name actually into the chat box, and then I'll call on you to ask a question, and maybe I'll just get us rolling. The middle part of your talk, Will, where you talked about these time-resolved microscopy experiments where you measured directly diffusion lengths on the perovskite.
Yes.
What happens if you take those values and you compare to conventional charge transport where there's an electric field also? Can you rationalize the results you get in terms of mobilities and mean free paths from conventional charge transport?
Yes, that's the long and short of it. Yeah, the mobilities are comparable to what are measured in in Hall effect measurements. For instance, the more relevant thing from the standpoint of a solar cell is not the mobility, but the minority charge carrier diffusion length, which has contributions from the mobility and the minority carrier lifetime. We are in a bit of a different excitation regime. You know, we try to be as unperturbative as possible in the sense that we're doing low injection, but we are photo exciting the system much more heavily than would be excited under terrestrial solar fluxes. You know.
Okay.
So there is a bit of a difference there. There's lots of great questions over the coupling of halide anion segregation to optical excitations. This formed a internally consistent study. I'm hesitant to draw too many conclusions beyond what we studied here, but the mobility values are consistent to answer that simple question.
Okay. All right. I have a bunch of other questions, but maybe we'll go next to Dan Frisbee.
Hi, Will. Nice talk. My question is, what's known about the elastic properties of these perovskite materials, and how does strain affect the optoelectronic properties? Is that known?
Yeah, that's a good question. So as far as the elastic properties, I can't tell you. We've been also working on thermal transport, which is a separate story that's not here. Strain is clearly important. It manifests in the stability of the materials. There's a difference. There's very much difference in the performance of if you've got methylammonium as your cation, formamidinium as your cation, cesium as your cation. And you see no shift in the band gap. You see a negligibly small shift in the band gap. But you do see things like the photoluminescence quantum efficiency changes dramatically depending on what organic cation we're using, even though the color of light being emitted is not different. And so we think that these are all secondary effects of the size of the organic cation is changing the distortion of that perovskite unit cell. There's been a lot of correlation paid to, if you've got these two lead halide octahedra, they can rock and tilt. That out of plane distortion is correlated with the formation of so-called self-trapped excitons, where basically a polaron so strongly distorts its local environment that it creates its own defect in the crystal and creates a much lower energy, broader emissive species that is not desirable for a light emitting application, for instance. So all that is to say, from a ground state perspective, I don't know much about the elastic properties. From an excited state perspective, yes, the strain induced by the steric hindrance of the organic layers seems to have a lot to do with the sort of secondary optoelectronic properties of the material, not directly the band gap so much.
Thanks.
Dave Flanagan has a question.
Hey, Will. Awesome talk. Really, really cool stuff. I'll keep it short because I think we're running a little long, but because I have a ton of questions. But how are you actually able to disentangle the influence of grain boundaries and composition on the electronic properties? I followed the story of the cation and the role, or maybe no role, that it plays on the electronic properties. And I was thinking in the early part of your talk, that's potentially what you're seeing when you don't see any influence of composition on carrier properties. But I'm wondering how you're actually able to determine, is it the grain boundaries that are playing the role? Is it the composition, or is it a synergistic effect? I didn't quite catch that.
So first thing I'll say is we make two observations. We make the observation that in the single crystals, there's no dependence of the carrier diffusivity on the composition. And then we make the observation that in the thin films, the carrier diffusivity does depend on composition. That's as much experimental fact as we have. The rest of it is conjecture and hypothesizing as far as why that is. We also observe that in all cases, the diffusivity for the thin films is lower than it was in the single crystals. And so that suggests that in all, no matter the composition, the grain boundary is disrupting charge carrier transport. And then the next leap in logic is that, okay, perhaps these grain boundaries are having more or less of an effect on charge carrier transport, depending on the cation composition. The evidence that I glossed over or neglected to discuss at all are these Kelvin probe force microscopy measurements. So here's the AFM topography map of the binary cation and the ternary cation. And then the Kelvin probe force microscopy measurement is showing just at the lowest level greater differences between the grain boundaries and the grains in the potential in the binary cation than in the ternary cation. It's a more homogeneous landscape, which led to the hypothesis, okay, that these grain boundaries are acting as potential barriers. Some evidence for that came from this angle resolved emission, electron emission experiment, where we're looking at trying to get some depth sensitivity by looking at different angle emission of photoelectrons in this case. And we can map differences of, yeah, I honestly can't remember what that figure is trying to show. This was work that that Max Sood had done at Toronto, which is to some extent why I glossed over it. Not that I don't trust the results, but that this wasn't our direct contribution to the work, so I have a little more trouble owning it as my own work. But I'll stick to the observation. We make the observation that in the single crystals there's no dependence on composition. In the polycrystalline samples there is a dependence on composition, and that leads us to hypothesize that the grain boundaries are to blame.
Got it. Thanks, Will.
Okay, I think we're unfortunately at the end of the period of time we should take here. So please, let's consider this the end. I see some other questions though. So if people want to ask a question, want to hang on a little bit longer, I'm sure Will can give us a few more minutes and take some of those questions. And the first one actually is from Tristan Trutman. If you want to go ahead, Tristan.
Yeah, so in the first half of your talk, you talked about how you have these quantum dots that orient when the toluene evaporates. And I'm just wondering, can you talk about what drives that? How big of a role are the ligands playing, and how important are the facets in the crystals?
So great question, and I think you're exactly right. So you are thinking about all the right things. I can tell you, let's go back to, yeah, we'll look at this one for instance. So this was another thing I glossed over. So the ligands are absolutely essential. Without, so these are super lattices that we made from the same batch of nanocrystals. What we can do after we make the nanocrystals, we can treat them more harshly with non-solvent, which will strip off some of the surface ligands. And as the surface becomes as we do successive precipitations where we have lower and lower ligand coverage on the surface, eventually we don't get the formation of a superlattice at all. So you only get superlattice formation when you have a good coverage of ligand on the surface. That's the first thing I'll say. So the ligands are essential. But going to your second hypothesis, just having ligands on the surface doesn't tell you anything about why you should get any particular orientation. Yes, I think this has everything to do with the faceting of the nanocrystals. My particular hypothesis is that this has to do with differences in the ligand binding energy, ligand binding density on different facets, that even if you have ligands coating all surfaces, but you have a different density of ligands per unit area on two different surfaces, that effectively leads to a different compressibility. And just that difference in compressibility or the elastic properties along one particular facet versus a different could lead to this ordering behavior. And this is what Sam is trying to model here in this coarse grain representation of a quantum dot, where he has different ligand spheres with some characteristic interaction potential that is bound to different facets of the nanocrystals. But yeah, I mean, at some level, it has to be the facets. Ligands alone won't give you any particular epitaxial orientation.
Mm-hmm. So by that hypothesis, if you were to grow these crystals in an ahedral environment where they're perfectly spherical, would you still get this orientation effect?
I do not think you'll get the orientation effect. I skipped over some of my literature review. You still get this big interplay between BCC and FCC. This is sort of an age-old question in colloidal assembly, that what is the lowest energy structure? And there's been a lot of work in gold nanocrystals that are much more isotropic and spherical in shape, that there's a strong dependence on whether you get a body-centered cubic or a face-centered cubic structure, depending on the ratio of the ligand length to the diameter. This is also theoretical work that Kamian Zerhel did in soft corona hardcore micelles, where they have depending on how soft your outer sphere of your colloidal particle is, that determines ultimately what the lowest energy structure is, whether it's FCC or BCC or even some Frank-Caspar phases that can be predicted. But to get back to your question, if this were a perfectly spherical nanocrystal, I do not think we would have atomic scale alignment between neighboring nanocrystals. I think that ultimately has to do with the faceting.
Okay, thank you.
Okay, Will, thank you very much. That was really fantastic. I think we ought to wrap it up. So thank you everybody for coming. And again, imagine more virtual applause that we would rain on you if we could do it in person. And your afternoon meetings, by the way, there are a different Zoom. So you're going to want to log off and come back to that other Zoom code.
Sounds good.
Thank you, everybody.